To repeat what I have been saying, we have been looking at the problem of two-body collision kinematics, where you have a target particle at rest in the laboratory frame, particle of mass m2, a projectile, a particle of mass m1 comes along with momentum p1 and hits it in an elastic collision, and the final outcome is that the target particle goes off at some angle beta with respect to the original direction with the momentum p2 prime, while the projectile goes off at some other angle alpha with a momentum p1 prime. And then according to Newton's third law, where action and reaction are equal and opposite, it leads to the conclusion that the initial momentum, the total initial momentum p1, since p2 is 0 to start with, is equal to the vector sum of the final momenta of the target and the projectile, p1 prime plus p2 prime. This is also an elastic collision in the sense that no energy is lost otherwise. The total energy, kinetic energy, remains exactly the same before and after the collision, and the initial kinetic energy was p1 squared over 2m1. The final one is shared between particle 1 and particle 2 and is this expression here. So subject to these two equations, we need to find out, for instance, what p1 prime is and p2 prime is in magnitude and direction. In other words, we need to find these magnitudes of these vectors as well as alpha and beta. Now, as I pointed out, when we resolve these vectors along the direction p1 and perpendicular to it, you have two equations respectively given by these two equations here. Together with energy conservation, they form three equations for four unknowns: p1 prime, p2 prime, alpha and beta, and there is no way you can solve uniquely for all four given just three equations. So what one does is to say, for a given value of one of the variables, and conveniently taken to be beta for technical reasons which I will mention later on, the solutions of these equations, simultaneous equations, are very straightforward. We saw this how to do this in a simple way. What you have to do is to simplify the algebra, define p1 prime over p1 is some x and p2 prime over p1 is some y, and then if you define the mass ratio r to be the mass of the projectile divided by the mass of the target, m1 over m2, then p1 prime has this solution in terms of beta, and p1 and p2 prime has this solution in terms of beta and p1. Moreover, the angle alpha is related to the angle beta by this expression here. This is an important expression. Sine 2 beta, tan alpha is sine 2 beta over r minus cos 2 beta, where r is the mass ratio here. So that's the conclusion we get. Those are the results we get for these dynamical variables after the scattering process. Okay. Now the task is to analyze these solutions. The first thing we notice is the following one, so let me write it as 1. In the one-dimensional case, in other words, when you have things moving along just one line corresponding to beta equal to 0, so the target particle just gets pushed along the same direction as the incident direction. When beta equal to 0, everything should reduce to the simple one-dimensional case that we have already solved. So it is clear immediately from this that p1 prime, for example, is equal to, if you took what the magnitude here is, it is m2 minus m1 squared, square root, so it becomes modulus. This is a magnitude, so this is p1 modulus m1 minus m2 divided by m1 plus m2. You recall that the exact solution is in fact in the one-dimensional case m1 minus m2 here without the modulus sign, because when m1 becomes smaller than m2, you could also have it moving backwards. It could bounce off the target and move backwards as you would physically expect. But these are magnitudes of vectors, so in this case strictly when you take the limit beta equal to 0, you get that solution there for the magnitude of p1 prime. p2 prime magnitude is 2m2 p1 over m1 plus m2, and of course you see from this relation that when beta vanishes so does alpha, so it immediately, so you have this, this and alpha equal to 0. So it checks. the one dimensional case emerges as a special case of the more general solution that we have got here, as it should. So everything is all right as far as this is concerned. The next thing to do is to check out what happens to these limits in the equal mass case. Suppose the masses m1 and m2 are equal, that means the ratio r is equal to 1, then you can immediately see that things simplify quite a bit. We take out an m1 squared here and write things in terms of ratio, or you set m1 equal to m2 equal to m and you pull it out, it cancels against the denominator and you end up with the equal mass case so you have m1 equal to m2 and the ratio r is equal to 1 in that case. Then p1 prime becomes equal to, well, you get a 2 from here and a 2 from here, so it's twice 1 minus cos beta, so 1 minus cos beta over there in this fashion, and you want a half to the power half divided by m1 plus m2. Well, m's go away, so there's just a 2 because the mass has been taken out common and cancelled against the numerator, and you have a 2 here. So this thing here is 4 sine squared out here. Sorry, this solution here is 2 this is 2 beta there, and the solution now becomes 1 minus cos 2 beta, and this is equal to 4 sine squared to the power half over 2 equal to with a p1 that's always sitting outside, p1 sine beta. Okay, and p2 prime is equal to this expression here, and the m cancels out on both sides, the 2 cancels out, and therefore you have p1 cos beta. So we have a picture which is remarkably simple in the equal mass case. In fact, if you see what alpha becomes, it's immediately clear. Alpha then becomes, this is sine 2 beta and this is a 1. So this is 2 sine beta cos beta divided by 1 minus cos 2 beta, that's 2 sine squared beta. So this is equal to cot beta, which is equal to tan pi over 2 minus beta. So it says alpha is pi over 2 minus beta, which is the same as saying that alpha plus beta equal to pi over 2. In other words, the scattering process looks like this. In comes this fellow, hits against this particle, this goes off at some angle and this goes off at right angles to it. So that's a right angle. This is 90 degrees out here, since alpha plus beta is pi over 2. So what happens in this equal mass case is that the target and projectile emerge at right angles to each other, although we haven't said, and we need more dynamical information to say whether it's like this or like this or like this and so on. So it's clear that the restriction alpha plus beta equal to pi over 2 is a very simple interpretation. It says this particle has a projection of P1 which is P1 cos beta, and the other particle has a projection which is P1 cos of this angle which is pi over 2 minus beta, so that's sine beta. So that's the reason why you get P1 prime is P1 sine beta and P2 prime is P1 cos beta, and the relation alpha plus beta equal to pi over 2 in the equal mass case. So that's a particularly simple instance. Just to check that the general result is right, it helps to write down what this does in that limit. Notice another fact here, and that is that you cannot have any value of beta beyond pi over 2. So what is happening is that you have a mass m2 here and you hit with a particle m1 with a direction in this direction. Therefore, there is no likelihood of this going backwards. It certainly cannot get to the left of this line at all. It has to move into the forward half plane in this case, and therefore beta cannot be greater than pi over 2, and that is immediately obvious from here, because this equation implies that beta is less than equal to pi over 2. Because if beta is greater than pi over 2, this backscattering here, then this becomes negative, but there is the magnitude of the vector p2, so it is not possible. So there is a limit on how big beta can be. It runs from 0 to pi over 2, as in that case as well. However, one can go further. One sees immediately that if this particle is heavier than the target particle, if the projectile is heavier than the target particle, it is unlikely that the projectile will come back. So in fact, it is much more likely that it will move in the forward direction, might not even reach pi over 2. And that is corroborated by the fact that there is a limit on alpha in the case when the ratio r is bigger than 1. So let us look at the case. So this is the next special case we want to look at. The next point 3, upper limit on alpha when r is greater than 1 or m1 is greater than m2. This means m projectile is greater than m target. Normally in scattering experiments, one is used to having a heavy target and a light projectile hitting it, but you could have the other situation when you have a very light target and a heavy particle comes and hits it. What happens then? There is an upper limit on this quantity alpha, which is found by taking this object here and differentiating with respect to beta and seeing if there is a maximum. So let us do that. So from this equation it follows that d over d beta tan alpha equal to the derivative of this quantity, which is 2 cos 2 beta over 1 r minus cos 2 beta minus sin 2 beta over r minus cos 2 beta, the whole squared, multiplied by the derivative of minus cos 2 beta, which is 2 sin 2 beta, and so let me put a square there. Take out the 2, so let us take out the 2, and this is equal to twice r cos beta cos 2 beta minus cos squared 2 beta, that takes care of this times that, and then minus sin squared 2 beta divided by r minus cos 2 beta, the whole square. So that is the derivative of tan alpha with respect to the angle beta, and in an extremum that is got to be equal to 0. So what does that tell you? It says alpha is at a maximum when alpha is maximum when this derivative vanishes and the numerator is r cos 2 beta minus 1, when r cos 2 beta equal to 1 or cos 2 beta equal to 1 over r. But cos of anything has to be less than 1 or less than equal to 1 in magnitude. So there is a solution to this, solution, a physical solution, only if r is greater than 1. That is precisely the case we are looking at. So when the target is lighter than the projectile, the conclusion is alpha cannot go beyond a maximum value. That is the largest it can be. And what is that maximum value? It is given by cos 2 beta as 1 over r. So let us write this maximum value down. It says the tangent of alpha, and let me write this as alpha max here must be equal to sine 2 beta, but cos 2 beta is 1 over r, so the sine is square root of 1 minus 1 over r squared, 1 minus cos squared, divided by r minus 1 over r here, which is equal to square root of 1 minus r squared minus 1 divided by r squared minus 1 equal to 1 over square root of r squared minus 1. So it says, and remember that r is bigger than 1. So this is a real number. It says this is the tangent of this angle, the largest value. Actually, it's more expressively done by remembering what the cosine and the sine become. So we have, in this case, alpha max here, and if this is 1, then this is 1 over r squared minus 1. That's how the tangent becomes this, and therefore by the Pythagoras theorem this is equal to r there. So the square of this plus that is equal to r squared, and this will imply that sine alpha max equal to 1 divided by r, or alpha max equal to sine inverse 1 over m2 over m1. So we have this constraint, we have this relationship which tells you the upper bound on the angle through which the projectile can be scattered after the collision, based entirely on conservation principles and the kinematics of the collision, independent of the dynamics. It says alpha cannot be bigger than sine inverse of this number m2 over m1, which is a number less than 1, because m1 is bigger than m2 here, and that's when you get the solution. For instance, it says, as an example, if m1 is equal to twice m2, then alpha max equal to sine inverse of 1 over the ratio, and the ratio, as you can see, is a half. M2 over M1 in this case is equal to half, so this is sine inverse half equal to 30 degrees. So it says that if you have a particle of mass m here and you're hitting it with a particle of mass 2m, then under these circumstances, if the collision is elastic, no matter what the dynamics of the collision is, this particle cannot be scattered anywhere greater than 30 degrees. The largest it can be scattered by is 30 degrees or less. So that's a kinematic restriction on the possible angle of scattering independent of the dynamics. Follows entirely from the law of the conservation principles of momentum and energy. So you see, you can get some fairly powerful results based on simple algebra and trigonometry using the conservation principles. So that was the lesson that I wanted to convey, that these conservation laws are very powerful in giving these limitations, possible bounds on various physical quantities. What about the energy transfer? That's another quantity we looked at in the one-dimensional case. We need to look at it in the higher dimensional case as well. Recall that P2 prime was equal to 2m2 P1 cos beta over m1 plus m2. In the case when beta was 0, it was 2m2 P1 over m1 plus m2. We already saw that in the one-dimensional case. So the energy transferred in E transferred is equal to P2 prime squared over 2m2. That's the kinetic energy of the target which was initially at rest. So this must be the loss in kinetic energy of the target part of the projectile particle. So P1 squared minus P1 prime squared over 2m1 is equal to this quantity here, and this is equal to, as we see now, 2m2 P1, so 2m2 squared P1 squared cos squared beta divided by m1 plus m2 the whole squared, which can also be written as equal to, I multiply and divide by 2m1 sorry, there is a 2m2, so this goes away out here because I divide by 2m2 here. So now if I multiply and divide by 2m2, this is 4e initial, which is of course p1 squared over 2m1 multiplied by 4m1 m2 over m1 plus m2 the whole squared multiplied by cos squared beta. So that's the exact expression for the energy transferred to the target from the projectile. Part of its energy is given out to the target. And now this relation is a generalization of what we had in the one-dimensional case, where this factor cos squared beta was missing because beta was 0 in the one-dimensional case. So we immediately see that E transferred over E initial is equal to a certain ratio of masses, which of course can be written as 4r over m1 plus r the whole squared if I pull out an m1 on either side and cancel the m1s, then this is what you get, multiplied by cos squared beta. And this quantity here, which is purely a function of the mass ratio, we saw what it did in the one-dimensional case. So to repeat that, here's r, here's this factor here. It starts off linearly with a slope 4r, and when r becomes much larger compared to 1, it becomes 4 divided by r, so it drops off like 1 over r with a maximum at the point r equal to 1. And if you plot the full thing for a cos squared beta included, then this maximum here, the value of this thing, so now we are plotting the full quantity. I am plotting this quantity now here, and this maximum value is cos squared beta. So it depends on what the scattering angle is, and it changes with the mass ratio, with the extra factor thrown in here in the general case as compared to the one-dimensional case. So we have a fairly complete picture of scattering, elastic scattering, under the assumptions we've made, namely that the collisions are elastic, no energy is lost, that it's a two-body scattering, that the dynamics happens in a very short interval of time. We don't care what the detail is, but we use the fact that action was equal to the reaction. In other words, we use the fact that the rate of change of momentum of the we simply use the fact that the momentum change of the first particle is related in a simple way to the momentum change of the second particle by just a minus sign in this case, which led to the conservation of momentum, which happens because we are independent. This whole process is independent of the absolute location in space of these objects. There is homogeneity in space, and then all these conclusions follow, including formulas for the scattering angle and so on. Now in actual scattering theory, there is another frame of reference as opposed to the laboratory frame, which is an extremely useful one, and I will just mention it here, although we won't do that very much at this stage, but we might talk about it later on. And that has to do with not a frame of reference in which you have one particle at rest and the other particle comes in. This is the lab frame, the laboratory frame, where the target is initially at rest, and in comes a projectile. There is another frame of reference where what happens is you arrange matters in such a way that by a translation of this, by shifting, by going to a frame which is moving with respect to these particles in such a way that particle 1 comes in this way and particle 2 comes in the other way. And it's called the center of momentum frame, because in that frame the two particles have equal and opposite momenta. So in this center of momentum frame the scattering happens with a vector p1 here and a vector minus p1 coming in from the other direction, and this is mass m1 and this is mass m2. I have used the same symbol p1, but actually it is in a different frame, so you can call it something else, but it does not matter. But these are the incident momenta, they are equal and opposite, so the net momentum is 0. Then by the conservation of momentum, which is still valid even in this frame, particle 1 may perhaps scatter and go off in this fashion, and particle 2 may scatter after the collision and go off again in the opposite direction. It has to do so in the opposite direction by the conservation of momentum. So this is P1 prime and this is P2 prime. This is M1 P1 coming in, this is M2 minus P1 coming in, and this one here is minus P1 prime. So we could drop this subscript 1 and simply call it P and minus P, and then P prime and minus P prime, and the problem now is to find out what this angle is. This is called the scattering angle in the center of momentum frame. Earlier we had two scattering angles, alpha and beta, but they were related to each other by that trigonometric formula we wrote down. On the other hand, here there is only one scattering angle because this one scatters by pi minus theta, while this one's direction has changed by theta here relative to its initial direction. This one's momentum has changed by the same angle relative to its initial direction, or pi minus theta with respect to P1 here. So the target now would be to find out what P prime is in magnitude and what the scattering angle theta is. Now I mentioned without proof here that there is a simple relation between that angle, scattering angle theta, and the angle alpha and beta that we talked about here. The reason the formulas were very simple in terms of beta and not in terms of alpha is because there is a simple relation between theta and beta, which takes a little bit of derivation. I am going to skip that, but because of this simple relation between these two angles, one very often uses beta in the laboratory frame in preference to alpha. Although they are completely equivalent, you could use either angle. It is easier to write things in terms of beta because of this simple relation between theta and beta. And the fact is that the whole scattering process, the kinematics of it, the algebra, becomes much simpler if you work in the center of mass frame, center of momentum frame. And that is the reason why physicists would choose that to work in, to compute quantities, and then after the calculation is done, you transform back to the laboratory frame to find out what the physical parameters are in the variables are in the laboratory frame here. Now it is particularly important, this frame becomes particularly important when these particles are moving so fast compared to the speed of light. They are moving at appreciable fractions of the speed of light, that you have to replace the Newtonian equations that you have here for momentum and relation between momentum and velocity with the relativistic equations, and they are a little more involved and complicated, but once again the algebra becomes simpler if you work in the center of momentum frame. I must mention here, simply mention, that even with special relativity, even in the presence of special relativity, the conservation principles of energy and momentum continue to hold good for the same reasons for which they hold good in the non-relativistic case, namely the homogeneity of space and the homogeneity of time lead respectively to conservation of linear momentum and the energy, and those continue to hold good, as also the conservation of angular momentum, which follows from the isotropy of space. So these are the some of the elementary applications of these conservation principles, but they are used in a huge variety of contexts, and when the occasion arises, we will call these back, we will come back to these principles here and see how they are used in other applications.